All right, so we're going to be doing the projectile motion lab, and there's a lot of stuff that I want you guys to do. So I have it broken down into two big tasks, and for each of those tasks, you're going to be going to the PhET website, and you're going to be using a simulation that I will show you here. So this is the simulation, and when you first boot it up, like you'll go to here. When you first boot it up, it's going to give you some choices. The intro or the vectors. These are all things to kind of play around with. They're kind of cool, but most of what you're going to be doing is in this lab thing, hence the name. And you can see that what you've got is a cannon that can fire cannonballs, and it will trace out the path taken by those cannonballs. You can change the angle that you shoot the cannon at. You can change the velocity that the cannon shoots with. You can also change a number of other things. You can do things like changing the mass of your cannonball, the diameter of your cannonball. You could change the acceleration of gravity. You could turn on the air resistance on or off. All kinds of cool stuff you could do. And what your goals are twofold, right? In the first task, I want you to make a series of shots. And that means you're going to probably have to plan, like, what angle do I shoot at? What velocity do I shoot at? And that sort of thing. And the three shots that I wanted you to make were, I've already forgotten. That's crazy. So you want to have the first shot hit the bullseye 15 meters away from the cannon. The second shot's going to hit that same bullseye at the same location, but it also has to reach a peak height of at least 8 meters along the way. So the first shot doesn't have a height restriction. The second one does. And then the last shot, I want you to shoot the guy with the stupid looking shorts. This little statue of a guy here. This is an HTML5 version of an older simulation that was there a few years ago. And unfortunately, the old simulation, when you shot the guy, it was funny. His shorts would fall off and he had a little fig leaf, and it was kind of funny. It made like a little noise. This one here, it doesn't do anything when you shoot him, so I was kind of disappointed. But we're going to shoot him anyway. But you're going to plan those three shots out, and what's going to happen is you're going to have to take those three shots in a row. So, like, if I fire a shot, it'll leave a track for where it went. If I change and fire another shot, I'll see that track as well. Right? If I want to erase all of my previous shots, I can hit this reset button and start from scratch. And what you're going to have to do is, in your lab report, I want to see a screenshot of each of those three shots. One shot hitting the targets, another shot going at least 8 meters high, which is going to be somewhere up here, and hitting the target, and then the last shot hitting the target of the dude. And I want to see all three of those traces with no additional shots taken. So what you won't be able to do is just fire a bunch of test shots randomly until you zero in on one that works. Right? You're going to have to plan this out. So, yay, I hit the target, but you're going to want to be able to do the math to figure it out, because now I can't guarantee that if I change something, it's going to work as well. I want to be able to do all three shots at once and have only those three shots showing in my screen share. So you're going to have to do the math to figure it out rather than rely on trial and error. So that's your first objective. Your second objective is to think about the functional relationships between the vertical range, that's the horizontal distance traveled by your projectile, and any number of other confounding factors. Now, what we did in class the other day was we ended up deriving the range equation. And the range equation, if you recall, said that the horizontal distance that this thing would travel if you fired it ended up being V initial squared over G times the sine of 2 times whatever angle you shot it at originally. But this equation is only true with no air resistance. Ah, can't write today. Air resistance. So we know what the answer would look like if there isn't air resistance. But what we don't know is what would happen if I have the air be difficult to push out of the way. How will that affect my answer? Would I have a different equation? And what would that equation look like? And here's the thing. I don't know the answer to that. I couldn't tell you what the equation is. I can't tell you what the right answer is off the top of my head. But I have some ideas of what the answer might look like based on experience. But in actuality, if I were to try to derive mathematically what that equation was, that's a graduate school level problem that we're not going to do. But we do have the capacity at this level to experimentally produce an equation, or at least parts of an equation. And that's what I'm asking you guys to do. So how are you going to pull that off? How am I going to do this simulation in such a way that I can determine what the equation might be for the horizontal range if I include air resistance? Well, what you can do is you can make plots. So for instance, right now I have the air resistance button ticked off. And if I set the initial velocity to some number and I leave that number alone, and I set my initial angle to some number and I leave that number alone, if I fire this thing, it's going to land a certain distance away. And I've got this groovy little meter that if I hover it over where my thing lands, it'll tell me, aha, it traveled 11.3 meters. So with a mass of 17.6 and a diameter of 0.18 meters and an initial speed of 18 meters per second, and all these settings, the angle of 80 degrees, that's how far it went. But what would happen if I were to change one of those parameters? Well, let's try that. Let's leave everything here the same except for one thing, right? Let's change the mass. I'm going to crank the mass all the way up. Now, when I fire the cannon again, what you see is that the cannonball landed in the exact same spot.
Dr. Fleming, are you supposed to be showing that screen that you're doing right now?
Absolutely. Are you not seeing that screen?
No, we see you.
Well, that's retarded. Okay, I'm stupid. Let's try this again, only this time hitting the buttons. Thank you for speaking up, because I would have prattled on for an hour.
Kept going. Yeah, I was like, I can't see what he's doing.
Like, yeah,
okay.
I didn't even realize. Okay, so let's try that again. So I fired it once. Cannonball lands someplace, right? I've got this groovy little tester, and if I put it next to the cannonball where it lands, it tells me where it landed, right? Now, if I go over here and I adjust the mass, here's the air resistance is turned off, and I fire it again, that cannonball lands in the exact same spot. If I crank the mass all the way down to 0, well, not quite 0, to 1, it lands in the same spot. So apparently, with no air resistance, the mass of the ball doesn't matter. And that shouldn't be super surprising, because we already know what the equation should be for no air resistance, and this is it, right? Notice the mass doesn't show up in that equation at all, right? That's why we could change the mass over and over and over again, and as long as we didn't change the starting velocity or the angle we were shooting it at, it always landed in the same place. However, watch what happens when I turn the air resistance on. All right, I'm definitely sharing the stupid screen again. So I'm going to leave this up here for comparison purposes, but let's click this air resistance button. And right now I have the mass set at 1 kilogram. I'm firing. Well, that made a huge difference. Before, it was always traveling 11.3 meters, but now it's only traveling 9.52 meters. So with a mass of 1, I got a distance of 9.52 meters. That's a data point. Does that make sense? What about if I take the mass up something higher?
I have a question. Are you picking the mass
Yeah,
or are be given?
you see the slider? I'm picking it.
Okay.
So I had the slider at 1, the first shot. Now I'm going to increase it up to some different mass. I have it at 5.96. And I'm going to try that and see what difference that makes. So when I raise the mass up to 5.96, oh, look, it went further. How much further? 10.95. So you'll notice that already we're getting pretty close to what it would have been if I hadn't had the air resistance on at all. Let's crank it all the way up to the top. Well, gosh, I can barely tell the difference between that shot. It looks like it went 11.23 meters at 31 kilograms. And I could probably take more data points. I'd love to have some of them land somewhere in here. But if I was looking to figure out what the equation might be, I have a bunch of data points. And I'd like to be able to see if I could derive what the equation is. So how do I determine what the equation is between those data points that I just took? So I just really quickly, come on. There we go. I really quickly just made a little table, right, while I was doing all that. And if I want to know what the equation is, the best way to see that is a graph. All right. Now, had I graphed it without air resistance, what would that have looked like? So I'm changing the mass. So the mass would be my independent variable. And I'm plotting how far it traveled at the end. So that's my dependent variable. And if I had done the original, then I got the same distance for every single one of them. I would expect to get a straight flat line with no air resistance. But with air resistance, I'm not going to get a straight flat line. Instead, what I'm going to get is when the mass was super, super big, it went almost as far as it did before. So it's going to start out looking very much like that. But as the mass gets smaller and smaller, and ends up big. When the mass gets smaller, the distance was getting smaller. So I expect a graph that looks something like this. Maybe like that, I don't know. I would plot that out. That function would help me make a guess about what the equation might be. Does that make sense? Let's plot it out. If I go over to my screen share again, this sounds like a job for Excel, so let's use an Excel file. So I plotted my mass in kilograms and my range in meters. So I had 1 and 9.52. I had 5.96 and 10 point, is that a 9? I think 9.5. I had 31 and 11.23 and 8.71 and 11.04. And so if I were to do a graph of this, what you can see is that it looks like it's kind of flat and then it drops off rather drastically. And maybe I want to fill in some of these gaps and make it a few more data points. But the idea is that at that point, I can speculate as to what sort of function might make a graph that looks like that. It's terrible. So what sort of mathematical functions or equations might give me a graph that looks like that? I don't know.
So this is considered to be inverse of half parabola?
I don't know. It might be. I don't think it will be. It's more than likely this is gonna be something that's like if I had to guess, it's gonna be something like some number and maybe 1 minus something that gets smaller as x gets bigger. So like, 1 over x squared or something. So what's going to happen is when x is really, really big, this term here gets tiny and it approaches the value of whatever a is. So maybe a is like 11.23. But when x is super, super small, 1 over a tiny number gets really, really big. And that's why it starts to drop off. So if I had to guess, I might guess that it's something of that form. But that's just a wild guess. And right now, we don't have the tools to make any kind of better guess. We'll learn more about how to make guesses later, but we'd have to have more to work on with theory. And so we'll probably revisit that question. We'll look at your results later on when we get to chapters 4 and 5, because in chapter 4 and 5, we're going to learn about the physics of air resistance. So right now, I don't expect you to know conclusively what this equation is going to be, but it's got to be an equation that looks sort of like that. And yeah, you might think that it looks kind of like a sideways half parabola. And so something else that you might guess that it's something like y equals the square root of x, because that would also look like a sideways parabola. But I suspect that this is leveling off to a constant value, and this would not. This would keep getting bigger and bigger and bigger forever, just getting bigger at a slightly decreased slope. So I would probably rule that out. But right now, I just want you to find the functional relationship, and we can speculate as to what the equations are at a later point in time. Does that make sense?
Yes, thank you.
Yeah. So all I can say conclusively, looking at this, is that clearly, as the mass gets larger, it's starting to flatten out and approach a constant value, but it's getting smaller and smaller and smaller as the mass gets smaller. Stop. So you're going to do that.
So that's the air resistance exists or without air resistance?
This right here is with air resistance. Without air resistance, then what would have happened was, without air resistance, we've already seen that it would have just been a horizontal line.
Okay.
And here it's like it's close to that horizontal line, but as the mass gets small, it deviates away. So the physics down here is different from the physics up here.
Okay.
And I'm looking at you to qualitatively judge that rather than quantitatively. So, you don't have to feel like you have to fit the curve. We haven't learned how to do that yet. We'll do more of that later. Now, what about the other things I've asked you to do? Well, I've asked you to determine the functional relationship between the maximum horizontal distance and the diameter of the object in the presence of the air resistance. We saw that it didn't have any effect when the air resistance was off, but will it have an effect when it's on? I also want you to look at the initial velocity. And so in each of these experiments, what you're going to be doing is you'll be keeping everything the same except for one thing that you're changing. and you want to see how that impacts your results. And once we get to chapter 5, we'll learn more about air resistance. We'll be able to possibly look back at your results from this lab and see if we can't make them make sense with what we learned then. All right. Does that make sense? You guys follow what I'm asking you to do? I will take the silence for a resounding yes. Yes,
I
Tom.
think I do, but I'm not 100% sure.
Okay.
I was about
Well-
to say, I maybe need to a little help outside of the lab, because it's like I get it, but I don't get it.
Well, part of it is one of those things, like try playing around with it and taking some data points, and then I can help you interpret those.
Okay.
In other words, you know, to some extent, you're just going to learn by doing. As for the first objective, you know, that's going to be solving projectile motion problems. And there's a pre-lab question or a pair of pre-lab questions that hopefully will get you thinking about how to approach those issues. So do the pre-lab questions first. They're just straight up projectile motion problems. And hopefully that will get you thinking in the right way for solving those bits.
Okay, thank you.
Yeah, you're very welcome, guys. So at this point, you know, if you want to break out into rooms and work amongst yourselves, you're welcome to do that. If you want to do this offline, you can do it offline. But I'm here, so I will answer any questions you got.
Dr. Fleming, can we go over the lab that's due tonight?
Yeah, we can talk about that really quickly. What's your question?
Okay, so for the last 2 objectives, I know that we're using one of the 4 kinematic equations to, like, you know, come up with like the position and the velocity. But for the first 3, are we just plugging in numbers to the simulation, or are we supposed to do an equation to come up with the graph?
Let me double check which objectives were which. I don't remember. So yeah, so for this one here, what you were trying to do is you were generating the parameters that would make that happen.
Mm-hmm.
So for instance, in objective 1, I want to make a position graph that curves upward like a parabola.
Mm-hmm.
So looking at that, what can you tell me about the velocity of the moving man or the acceleration of the moving man? How do you get any information about that just from looking at that graph?
I guess the velocity, I know it would be positive, and the
Okay, why do you say
acceleration
that?
because it's going upward.
Okay, that's good. So the position is getting bigger. It's becoming more and more positive. So it's got to have a positive velocity. I like that thinking. That's so far so good. The velocity's definitely got to be positive. What else we got?
And I would start the position at the bottom at 10, since it starts at the bottom and curves up.
Well,
think.
let me look here. Like at time 0, the position looks like it's 0, right?
Wait, Dr. Fleming, are you supposed to be showing the screen? Because it's not
Oh
showing.
shoot, I thought I was. Darn it. Yes, I thought I was showing the screen. All right. So look,
Okay.
right here at time 0, the position equals 0, right?
Mm-hmm.
So the dude's got to start off at 0.
Okay.
All right. So I'm starting him off at 0. Now, what about this graph tells me the velocity?
The slope.
The slope. So what can you tell me about the slope of that graph?
Is going up.
Yeah. So it's a curve, right? Curved lines have slopes that are continuously changing.
Mhm.
So unlike a straight line that has one slope the whole time, this has a slope that keeps getting different. That means the velocity is going to keep getting different. And the way you do the instantaneous velocity is you take the slope of a tangent line. So like right here at this point, what I would want to do is find a tangent line, and that would look like that. So that's a horizontal line, right?
Mm-hmm.
That tells me that my dude has to start with a velocity of 0, because that's the slope of 0.
Okay.
However, if I look at him later, like say right here, now the tangent line is steeper. So what's happening is his velocity starts out at 0, but it's going to get bigger and bigger and bigger as it goes. He's got to be accelerating. And the fact that this object, this curve is curved and it's concave up tells me his acceleration has to be something positive. So what I would do, knowing that, is I'd go to my little moving man sim. And I would wait a year for it to load.
Mhm.
Come on. You can do it, little computer. Or not, you can't. Oh, here we go. All right. So I know I got to start this guy with a velocity or a position of 0. He's got to start at 0. I'm starting him with a velocity of 0. So I'm going to make that be 0. But I need his acceleration to be something positive. So I'm just going to pick a positive number. Like, I don't know. Oh, I got to go to charts. Let's go to charts. So starting with 0, starting at 0. Let's make his acceleration be something positive, like 2. Right? Let's see if it worked. So now I'm just going to set him up, let him go. And would you look at that? So lo and behold, what's going to happen is while he's moving, I got that nice, happy, parabolic looking curve exactly like I wanted. Notice that what's happening is because my acceleration is 2, like the acceleration is 2 the entire time, this right here has a slope of 2 the entire time. And this has a slope that starts off at 0 and gets bigger. Whatever slope it has is the value of this graph right here. Does that make sense?
It does.
Well, I'm sorry. Oh, sorry.
Go ahead.
Well, okay, so I'm sorry. Let me gather my thoughts real quick.
Okay. Somebody else was speaking while she's
Yes.
thinking.
I just trying to figure out like why the position graph like going to curve instead of straight. I mean, the position graph goes to curve and then the velocity goes to straight line.
Because remember
Wow.
the definition of velocity is the rate of change of position, right?
Yeah.
And the rate of change of velocity is acceleration. So what's going to happen is if I need to change chairs again. All right. So we know that velocity is delta x over delta t, right?
Yes.
Now, if my graph is a position graph, then delta x is the rise and delta t is the run.
Mhm.
So if I have a graph that's straight, the slope of that graph is the velocity.
Yes.
By the same reasoning, acceleration is delta v over delta t. So if I'm looking at a graph of velocity, the slope, the delta v is the rise, delta t is the run. So the slope of the velocity graph is equal to whatever the acceleration is. So what did I do when I just set that simulation up? I told it to make the acceleration of that dude be 2, right? I just flat out said his acceleration is 2, and I started with his velocity at 0 and his position at 0. But what's going to happen is because the acceleration was 2, the velocity and the acceleration both changed as time passed on. So if you look at the 3 graphs we had, the acceleration graph was 2 the whole way. At any given point in time, A was 2. It never changed.
Mhm.
However, the velocity graph was a straight line. And what's more, the slope of that straight line was 2, because everywhere I looked, the acceleration was 2, so this had always a slope of 2. Does that make sense?
Yes.
But the position graph, the value of this graph has to be the slope, or the slope of this graph has to be the value of this. So at first, the velocity was 0, right? At time 0, this graph reads 0. So I started off with a graph that had a slope of 0, which is horizontal. But a split second later, the velocity is not 0 anymore. It's a little bit. So it had to be curving a little bit upward. But then a split second later, the velocity got bigger, so the slope had to get bigger. So what's happening is it started off flat, but it gets steeper, steeper, steeper continuously. Because the number on the y-axis of this graph keeps getting larger, so the slope of this had to keep getting larger. Does that make sense?
Yeah, I mean, the question is, I just couldn't figure out, like, why is that being a curve?
Well, it's because the velocity wasn't constant. Here, the acceleration was the same number the whole time,
Yes.
which means this graph had one slope the whole time.
Yeah.
Here, the velocity keeps getting bigger. That means the slope can't be one number the whole time. It can't be straight. It's got to be curvy.
Okay. Yeah, that makes sense.
By
Okay, I have a
comparison,
question. Oh, sorry.
go ahead.
So my question is, when we do this on the simulation, are we like screenshotting that and putting?
Yeah, that's what I was asking you to do. Yes.
Okay,
And
I was just making sure.
You'll tell me, like, in your data file, you're not recording a whole lot of data. What data would I have to record there? Well, I would record that I gave him an initial velocity of 0, an initial position of 0, and an acceleration of 2, right? Those are the numbers that I picked.
Okay.
And here's a screenshot. That's it. So you didn't do a whole lot of calculations or math. Mostly it was just figuring out what my setup had to be and then implementing it.
Okay. And my last question is the one where we have to use the equations to figure it out. How we go about that. I think that's
Well, for each of these, you're thinking through the process the same sort of way. So, like for this one here, what are you going to do for this one here?
the slope.
No, I'm asking, what are you going to do to make it happen?
Oh, use
What
the
parameters are you going to have to fix?
The position.
Isn't it velocity?
Well, this is a position graph.
So the
So what's the moving-
acceleration.
So what's the moving man got to be doing in that objective?
Decelerating?
He's going down in negative direction.
Yeah, he's traveling in the negative direction, right? This is a straight line with a negative slope. So what that tells me, see if I can do this without switching cameras, is that this guy has a velocity. If I did his velocity graph, it's got one negative slope the entire time. So it would be below 0, but the same value. So here's 0. It's going to be negative something. It's going to be straight. Does that make sense?
Yes.
What's his acceleration graph going to have to look like? Well, the acceleration graph would be the slope of his velocity graph. What's the slope of this?
Zero or
Yeah.
whatever negative number. Oh.
Nope, it's definitely, you're right the first time. It's 0. That's a 0 slope. So that means his acceleration has to be 0 the whole time. So to set up the moving man to do that, what I'm going to do let's clear all those drawings. So
Oh, no,
what I would do is I would reset all of this.
Excuse me. I have another question. So when we're screenshotting it, do we use the like the print screen
fine.
like that feature? Okay.
Yeah, that's fine. However you want to get a screenshot, go for it. Just make sure I can read it. So for this guy, he had to start off with a position that wasn't 0. So I'm going to start him off at something big. I'm going to pick 10. Right? But he has to have a negative velocity. Let's have his velocity be -5. And his acceleration's got to be 0. And notice we're getting exactly what we said we were going to get. And I'm going to stop him right there. Stop him, yeah. So look, I got a graph. The position graph is a straight line that slopes down and to the right. The velocity graph is one number, it's -5 the whole time, and the acceleration is 0 the whole time, just like we predicted. So that's the way you got to think about each of those. So let's skip objective 3 for a second, and let's talk about the numerical ones that are different for objective 4. So for that one, the moving man has to begin to move. I have to make him move, begin at the house and move towards the tree, and turn around just as he reaches the tree. I thought we did that one in class.
Yeah, we did it already.
Okay. So what we did was like, oh, well, where's the tree? The tree's at -8. The house is at +8. And so we had to do some thinking about what that was going to look like. So I've already forgotten what we were doing. So he's beginning at the house and traveling toward the tree. So here's the tree at x equals -8. Here's the house at x equals +8. The dude starts here. He travels this direction. He turns around when he gets here. So when the guy gets to the tree, he's got to have a velocity of 0. Does that make sense?
Mm-hmm.
So for that one, I'm turning it into a simple kinematics problem. His starting position, he started over here at 8. His ending position has to be over here at -8. He's got to be traveling towards the thing, and I don't know, it doesn't matter what velocity he starts with. I just pick a number. But depending on what I pick, I might have to have a different acceleration. So if I pick him to start off traveling at a speed of, let's say, -10 meters per second, when he gets here, he's got to have a velocity of 0. So I freely picked this, but all of these I couldn't pick. They have to be like these are all mandated by the problem. Now, the acceleration I don't know, and the time I don't know. And I can control this. So I've got an equation where I'm solving for A. I don't care about T, and I'll make that work. So the equation that doesn't have time in it is the stopping distance equation. Right? And for this value that I picked for V initial, I can solve for what A is going to make it work. So V final's got to be 0. So I'm solving this for A, so I'm going to move this over. So -V initial squared equals 2AX minus X initial. I'm going to go ahead and divide by 2 and this. So I have -V initial squared over 2x minus x initial. So that's the acceleration I'm going to have to pick. And for the values that I picked, what does that work out to be? So I'm plugging in -10, and notice this is tricky. This is -10 squared, which is +100, times -1. So that's going to be negative top. On the bottom, it's going to be x final, which is -8, minus +8, which is -16. I'm going to have a negative over a negative. I'm going to get a positive answer. And I get 3.125. So if I pick this to be my V initial, that's the acceleration that I'm going to have to pick to work with it. So now, having made that prediction, I can go back to my other screen share. I'm remembering to share it this time because I'm not stupid. Yay. And I'm going to go back to my moving man. I'm going to reset everything. And I'm going to start him at a position of 8. I'm going to give him a starting velocity of -10, but I'm going to give him an acceleration of positive 3.125. And so now, as he gets closer and closer to the tree, he's slowing down more and more and more and more. And what ought to happen, if I did my math correctly, is he's going to get to that tree and turn around. Now, I didn't have to pick my starting velocity to be -10. I could have picked any negative number. But if I'd had him start with a slower starting velocity, I would have had a smaller acceleration, and it would have taken him more time to get to the tree. Does that make sense?
Yeah.
And so for the last one, you'll do the same trick, except in that last one, you're asked about,
I
okay,
have
so
a
begin at
question.
the tree and come to a stop 3 seconds later. So there, I've told you the time. You're going to still choose an acceleration that makes it work, but it'll depend on what velocity you start him off at.
Okay, I have another question. For objective 5, I achieved like getting him from what was the tree to the house in the 3 seconds, but I didn't have to put in an acceleration. And then when I used one of the equations of motion, it gave me the acceleration of 0, but it was like, it was still the same. So do I need to have
So you had him, but I thought in objective 5 he had to stop at the house.
Right.
Well, if you don't put an acceleration in, he won't stop.
He stopped at 3 seconds.
Did you pause the thing, or did he actually come to a velocity of 0 at that moment?
Let me do it again.
Yeah, because if you don't give him an acceleration, he's going to have a speed. It's not going to change. So he's going to get to the house. He's still going to be going.
Okay.
The acceleration is there to make him slow down so that his velocity will be 0 for just a moment. He'll turn around just like he did in the one we just did.
Mm-hmm.
It's going to be the same thing we just did, except you've got to solve for t instead of solving for a. Or so you have to solve for a, but you know t, you don't know v initial.
Okay, and last question. So for the procedure, can we just say for the graphs that we kind of eyeballed what numbers to use, and then that's the numbers we used?
Right.
Okay.
A lot of times when you're doing an experiment, you've got to make choices about like what something had to be. So like in that example we just did, I chose for him to start with a velocity of -10, right? Now that choice was utterly arbitrary. It didn't really matter what number I picked so long as it was negative. So in your procedure section, what you might say is, we chose to start him with a velocity of -10 arbitrarily. He had to have a negative velocity, but any negative velocity would have worked. However, we calculated that with a starting velocity of -10, that would require that he have an acceleration of 3.125. Right? So as long as you're explaining why you're making those choices, you're going to get the points for justifying why you did stuff. Because that's what I'm looking for is, it wasn't like you had to have a velocity of -10. You could have picked any number, but once you pick -10 as your velocity, that set what my acceleration had to be.
Okay, I lied. This is my last question.
Okay.
So for Word, we're going to be using the equation editor to draft up the equations, but in the data file, that's where we'll be showing the actual math.
Right. So like what will happen, let's go ahead and mock that up since this is new. So here's an Excel file. And let's imagine, I'm not sharing my screen again. I'm an idiot. Okay, let's try this again. I'm going to get good at this eventually. It's going to happen. All right. So let's say I'm doing the objective 4 part of your data file, right? So what did we just have for that? So I would have his initial position, and that was, what was it, 8?
Yeah.
Final position -8. And of course, if I was actually turning this in, I'd be way more careful with my unit labeling and my sig figs. So please bear in mind, I'd have to go back and pretty this up. Right now, I'm just trying to get it like out here.
Mhm.
The initial velocity, we chose that. To be, what did I say it was, -10 before?
Mhm.
But then we calculated the acceleration we would need, right? And the way that I did that was I had math. And so I'm going to put that formula in my Excel sheet. So when I want Excel to do math for me, I start with equals, right? Equals says do math and print the answer. And the equation that I had, I'm going to write it on the screen so you guys can see what I'm doing. So the equation we had was that the acceleration was negative v initial squared over 2 times x final minus x initial, right? That was the equation that I used. So that's what I'm going to put in that cell. So it's going to be negative. Now, v initial was cell B9, so I'm going to type negative B9 squared divided by, crap, I just did something rad. Oh, there we go. Divided by, now, this is where people often get in trouble. You see how I have a complicated stuff in the denominator of that fraction?
Mhm.
When you put a cell or an equation in an Excel frame, it's doing it out long ways. And order of operations would say that you do multiplication and division on equal priority from left to right. So if I were to just go divided by 2 times parentheses, see, x final minus x initial, and then I close it, I might think I'm going to get the right answer, but when I hit enter, it's telling me the answer is -800, and I know that that's not correct. The reason it's wrong is because Excel, it sees the thing that's squared, so it's going to square that first, get 100. Then it's going to take 100 times -1. Then it's going to divide it by 2 and get 50. Then it's going to take 50 times 16. That's why I got -800. But what it should be doing is it should be doing all the math on that denominator first. So what I have to do is anytime I have any kind of complicated stuff in the denominator, I have to put a set of implied parentheses around the entire denominator. So I'm going to put a set of implied parentheses around that whole denominator so that Excel knows to do that math first. When you write it out this way, it's obvious, but when you write it out in Excel, it's not. So I'm putting an extra set of parentheses around that entire denominator, and now I get the 3.125, except I've got a sign error.
So your printers will have to be.
There we go.
Okay.
So there you see that that's the formula that I did just longhand in my own work. But for my Excel reference, or for my data sheet, I want to have all the math there. Because what's going to happen is when you turn this file into me and I go to grade it, what I'm going to do is everyone's going to have a different initial velocity from you, right? You may not have used -10 for your velocity. Maybe you used your velocity as -5. Well, that would have been your acceleration. And notice how it did all the math for me because I put this formula in there.
Mhm.
So if I had picked -1, I would have had that acceleration. And by doing it generically, I can sort of do that on the fly. So what I'll be doing when I grade it is I'll hit Control tilde, and it will display the actual formula that you have in the cell so I can check to see if it's correct.
Okay.
And then if I go back,
I have a question.
yeah.
What did you do to fix your sign error?
So what's happening there is it's one of the things that Excel is it's trying to be smart. It's thinking that I almost wrote with a wet erase pencil on my screen. That's how stupid I am right now. All right, let's try this. So Excel sees that minus sign, and what it was doing is it was squaring it before applying the minus sign, but that's not what it should be doing. So what I did to fix the sign error was I made sure that it was -1 times the initial squared. So that way Excel knows to use order of operations and square that first, then multiply by -1.
Oh, so you just put -1 in front of the equal
Yes.
sign?
Well, I did. Look at you can see the formula that I put in if I highlight the cell. I just wanted to make sure that it wasn't squaring away that minus sign because that's what it was doing. So I just literally put in -1 times blah, blah, blah squared, just to make sure that Excel wasn't trying to get, wasn't thinking that the negative was part of the B11, because that's what it was doing. It was treating negative B11 as the number to be squared. But I wanted the B11 to be squared before I multiply by the -1.
Okay, gotcha.
So.
And we do this for each chart, right?
Correct.
Okay.
So like for the other ones, the ones like objective 1, you didn't do any math, right? But what you would do is you had to pick the initial position, the initial velocity, and the acceleration. And you could just type in those numbers. You didn't do any math for those, you just picked them. But you'd still want to record anything that you did. So like if you pick a number for any of those objectives, make sure that that shows up somewhere in your data table.
Okay. And that's when we screenshot the graphs and then put them.
Yeah. So what will happen is in your Word document, you'll have a screenshot of those graphs.
Oh, okay.
And if I wanted to see like, well, how did you get that graph? Then I can look at your data file and see, oh, well, they picked these accelerations for those graphs.
Okay.
Yeah. You probably would say like in words, because it wouldn't be too hard to say, hey, you know, we picked the initial velocity to be whatever in your procedure section. But in the results section, the screenshot of that graph is all you really need, because that was the thing that I asked you to do.
Okay, and I have one last question. So I know at the beginning you were saying something about our units.
Mm-hmm.
So do we put what units it is, where the
Right,
initial
so
position is?
Yeah, like so for instance, here where I was doing this really quickly, I said initial position and I didn't label the units at all. But what units were those in?
Meters.
Yeah, if I go back to the moving man simulation just to verify, you can see these are definitely in meters. So
I would just make sure we didn't put them by the number, because I put it by the number and it had messed it up. So that's all.
Yeah, because so that's a common mistake. Let's say that you put 8 meters in here. Watch what happens to my calculation.
Yeah, that's what I was getting at first.
Yeah, because what's happening is Excel is stupid, right? It's trying to do math on the letter M, and it doesn't know how. So what you would instead do is only put a number in that cell, but then in the label where it says initial position, I might put parentheses meters, right? The final position, I do the same thing, in parentheses meters. And the initial velocity is obviously in meters per second. So, you know, the acceleration in meters per second squared. So make sure you label all of those things, because I should never have to guess what units something is written in. And it's super important. About 10 years ago, NASA launched a spacecraft that cost $127 million. And it burned up on launch. Because what happened was some NASA engineer made a mistake and they calculated something and they put in the mass of the orbiter, but they used pounds rather than kilograms. So because they did their math wrong, because they had the units messed up because they didn't label them well, this thing never made orbit. It didn't have enough thrust to get to the required orbit, so it just never made it to space. And that's $127 million of our taxpayer money that was wasted. You know, not to mention several years of a lot of these scientists' time, because, you know, some bozo wasn't careful about units. So being careful about units is important.
Okay.
So you guys have a sense of what I'm expecting here?
Yes, much better.
Yeah,
Cool,
much better
cool.
sense.
Awesome, awesome. So yeah, if you're ever not sure like what your data file ought to look like, don't be afraid to send me a draft and say, hey, am I doing this right? Or is this clear what I'm trying to say? I'm happy to give you pointers on that, because part of what I want you to get better at is writing technical papers. Many of you are going to graduate from JCSU and you're going to go on to graduate schools where you're expected to publish papers on your own. And you're going to have to learn how to talk about technical subjects in a clear and concise way. And it's definitely a process. It's weird because you're not used to writing like that. Most of your writing experience has been in, English classes where you're, telling me about this use of symbolism in Billy Budd or, stupid junk like that. So writing real papers is hard. Never want to have to read another paper about Billy Budd ever again. All right, so I think that we're set. I'm going to stop the cloud recording.